The final speaker today is Giancarlo Lucchini-Arteche. He will speak about the period index problem and Serre's conjecture 2 for complete discrete evaluation.
Thank you very much, Andre, for the introduction. Thanks, Danielle, and all the organizers for inviting me here. And thank you, everyone, for staying here. I know I'm a bit of an outsider to the main topic of this conference, and I know you all want to go to PPOLO afterwards, so thanks for staying here. I really appreciate it. So since I am a little bit of an outsider, I'll try to keep it simple. I really want to give you the main ideas of these two big problems and how they are related. And yeah, at the end, I have to tell you something I did with Diego Izquierdo. This is joint work with Diego Izquierdo from Polytechnique. But yeah, if you forget that, I won't judge you. So I want you to really focus on these two problems and how they relate. Okay, so let me start with the first problem, the first part of the title. So period versus index. It's a nice problem, very general problem that works for any field. So I'm going to fix K just a field, and K bar is going to be the separable closure. Okay. So you start with A as central simple algebra. So for those of you that might not know what a central simple K algebra is, well, there's lots of equivalent definitions, so let me just give two of them. For instance, this implies that if you tensor your algebra with K bar, well, then you get something that is isomorphic to a matrix algebra. That's one possible definition. Okay, so MN of K bar, or if you prefer, it's the same, it's equivalent, one can prove this. You can prove that it's isomorphic to a matrix algebra over D, with D a division algebra, K algebra, of course, with center K. Okay, so for instance, if you take the real numbers, you can have the quaternions, or basically any quaternion algebra over any field, number field, whatever, p-adic field, what have you, will work. Okay, so matrix algebras over division algebras work as central simple algebras. Okay, so this is the kind of things that you study by means of the famous Brouwer group, which you probably all know from your course on class field theory. So let me just define it anyway. This is a group given by central simple algebras over K, modulo some equivalence. And what's this equivalence? Well, we're going to say that the algebra A is equivalent to the algebra B, if and only if they are isomorphic up to tensorizing them with some other matrix algebra. Okay, so for some n and some m, you have an isomorphism after tensoring over K, of course, with some matrix algebra. So keeping this in mind and keeping this definition in mind, if you tensor this with a matrix algebra, you get just some bigger matrix algebra over D. So what this equivalence relation is telling you is that you should focus on the division algebra that is hidden inside a central simple algebra. So what the Brouwer group does is classify division algebras with center K over the field K. Okay? And this is indeed a group, because if you tensor two such algebras, well, this description will tell you just you're tensoring two matrix algebras over K bar, so you get, again, a matrix algebra. So it works. You get a central simple algebra again. And this is a way of sort of multiplying division algebras and getting division algebras again. That's what the Brouwer group does. Okay? So the best example that you probably all know are quaternion algebras. You can construct quaternion algebras, and these are just generalizations of quaternion algebras. And you can tear some quaternion algebras, and you get other central simple algebras. And then you're studying essentially the two torsion of the Brouwer group in the case of quaternions. Great. So if one wants to study these kind of things, there are two very nice invariants that one can associate to a central simple algebra or to the class in the Brouwer group. The first one is the period. So the period of A is just by definition the order of the class of A in the Brouwer group. Okay? So it's just the order. So for quaternion algebras, the period is 2. The other one is the index of the algebra, which is essentially the size of the division algebra. Okay, so it's the square root of the dimension over K of the division algebra D. And again, So you can see this one clearly does not depend on the class, on the representative of the class. It depends on the class. And this one as well, because again, the classes in the Brauer group classify division algebras. Okay? So, so both are invariants of the Brauer class and not just of central simple algebras. And again, for quaternions, as you can see, this is essentially 2. So period 2 for quaternion algebras, index 2 for quaternion algebras. So, okay, let's try to generalize this. So what is the relation between these two? Well, this is a fact that is well known. It was proved by Brauer himself. The period of an algebra always divides the index of the algebra. Okay, that's very nice. And they actually share the same prime numbers. Okay, so that we write it in this way. The index of the algebra divides some power of the period for some L natural number. Okay? So now, once you have that, well, you immediately start wondering, yes? Well, if you transfer it with itself, you will get the matrix algebra 4 times 4. So you get the trivial element in the Brauer group. That's an exercise. Nah. Yeah, it's not. Actually, a more nice exercise, a nicer exercise is take any central simple algebra, transfer it with its opposite algebra, just put the multiplication the other way around. That's also a central simple algebra, and you get a matrix algebra, always. And knowing that quaternions already satisfy that inverting the multiplication is itself, you get the, yeah, that's a nicer result. So that tells you that this is a group, because with all I said before, you only know it's a monoid. But it is a group. The inverse, the opposite algebra gives you the inverse. Okay? So great question. Okay, so you see this and you immediately start wondering, okay, what can we say about this L right here? And that is exactly the period index problem in general. So this is a naive, innocent question. Is there a bound for L depending only on the field? Okay, can we actually bound this L for every central simple algebra depending only on the field? And so these had led to many nice conjectures. Some of them had been proved, some of them don't. So let me just write some of them. I won't write them all because there's a lot depending on the field you're playing with. But okay, so let me focus on these ones. Let's just take L over K with transcendence degree, let's say n. Okay, so then, two cases. If K is algebraically closed, say for instance C, complex numbers, well then L should be n minus 1. Okay? What does this mean? It means that if you take, for instance, the field of functions of a complex curve, well, you expect L to be 0, so you expect to, no, not 0, that makes sense? Yeah. Yeah, that makes sense. Okay. And actually, yeah, if you take the function field of a curve over the complex numbers, you don't have a Brauer group. So it makes sense. Great. So you expect it to be 0. The Brauer group of a function field of a complex curve, it is trivial, so you can put 0 here and it works. And if you take a complex surface, you expect period to be equal to index, because you expect L to be 1. And this has been proved, actually. So this is OK if n is more or equal than 2 by de Jong. But again, it's open for n greater or equal than 3. So there you have some nice results you can try to prove. But since we are in a p-adic conference, let me now take a p-adic field. So if K is p-adic, well then you expect L to be n plus 1. Okay? So again, if I take a p-adic field, then I'm taking transcendence degree 0, so I'm taking L to be 1. So we expect period to be equal to index over p-adic fields. That is well known. Okay? Period and index coincide for p-adic fields. Okay? That's classic. But then if you take a p-adic curve, for instance, you expect the index to divide the square of the period. That's already known as well. So this is OK if n is either 0 or 1, so it's more or equal than 1. And the case of p-adic curves was done by Saltman. Okay, but again, p-adic surfaces, open. Yep?
And understanding the conjecture interaction between the first line and the second line, I mean, the big L and the second line, there is an implication, there is no.
Yeah, sorry, I mean, all this together implies this. Okay, but I'm going to use that line again in this case.
What is this L?
Just an extension with transcendence degree n.
L plus K?
Sure. Oh, well, yeah. If this is algebraically closed and you take an extension with transcendence degree 0, it's not very interesting. It's the field itself. Just ignore that case, please. Yeah, it's not a very interesting case. Yeah, maybe you should. Yeah, okay. Yeah, so I really want to study fields of geometric nature that, such as function fields of curves, surfaces, etc. Okay. So the point is, you would expect this L to grow with the transcendence degree. So if you have a field where you know what to expect, then it should grow by 1 each time you add a transcendental variable. That's what you should take from this conjecture.
Sorry, but you mean the Brouwer group of L, not of K, right? Otherwise, L doesn't have anything to do.
Yeah. Oh, yeah. Of course. I'm sorry. Yeah. That's really not well written. You're right. I'm sorry. Yeah. Should have put some L over there. I'm very sorry. Yeah. I should have. Yeah. Should have put that in the notation. I'm sorry. Thanks. Yeah.
No, it's okay. So it's just to the question. So you care about like how many times you should tensor an algebra with itself to get it trivial, right? But usually if you want to trivialize an algebra by like extension of the field, right?
Actually, they are all related. Yeah. You can prove. So the index, actually, you can prove it's the GCD of all the degrees of extensions trivializing your algebra. So that's the index. And the period, as you can see, it's not the same. It's kind of related. And this is telling you they are related, but it's a non-trivial relation. There's something there. There's something hidden. So this one has a more cohomological flavor because Brouwer group, as you all might know, it's a cohomological invariant. It's the H2 of the K-bar star. And this one is really algebraic, Diophantine somehow, because central simple algebras are related to Diophantine equations via the norm equations and stuff. So this is Diophantine, this is cohomological. There's some non-trivial phenomenon going on here in this relation. So it's interesting to understand it. Okay, so yeah.
When you write L equals n plus 1, you mean this is a bound or this is the sharpest possible?
This is sharp, yeah, it's sharp. And examples for that are known.
So L is the maximum possible.
Yeah, and you cannot get more, yeah. And actually, as I was saying, yeah, for surfaces, it's open, and the strongest result, so you expect to be, so you expect L to be 3, and it is known for 6. So 6 is a bound.
Okay.
And that was proved by, it's 5 people, Antio, Auel, Ingalls, Krashen, and Lieblich on the Invenciones some years ago. And yeah, getting 6 was already strong enough. So it's a really, really hard result. It uses the theory of twisted sheaves invented by Max Lieblich. So yeah, it's really, really hard stuff. Okay, so it was the first uniform bound anyway for p-adic surfaces. Okay, so that's pretty much the big problem. There's lots of techniques going on here, but I have to move on to the second problem. So the second problem is Serre's conjecture 2. So a priori, this has nothing to do with period index, but as you will see, there is a link. So K is still a field. And okay, so if K is perfect, then you can define, well, let me define it here. Now, the cohomological dimension of K, you can define it as, well, the minimum of the deltas in N such that cohomology vanishes in delta plus 1. So, and this is for every finite Galois module N. Okay? So the cohomological dimension is essentially where cohomology vanishes from now on. Okay? Great. That's for a perfect field. Okay? You can find this definition in Serre's book, classical Serre's book on Galois cohomology. But again, it's for perfect fields. If you start working with imperfect fields, already in characteristic P, you start finding some weird phenomenon where you see that the P part of this cohomological dimension behaves weirdly. It's always 1 or 0. So you start feeling that it's not the good invariant to keep track of the complexity of the field somehow. So you have to define something else. And the first one to come up with a definition for imperfect field was Kato. Okay, but yeah, I'm just going to say that the cohomological dimension of K is, well, something complicated. I don't want to write it down. It's really complicated. Okay, it involves differentials. Okay, I will say something about differentials afterwards, but you really don't need to know what it is. The fact that you have to keep in mind, though, and this is the important part, same paper by Kato where he defined this, he proved the following theorem. So again, I'm going to write here, this is Kato. And probably this is the point for defining this complicated definition, is in order to get this result. If you have K complete and discretely valued, so complete with respect to discrete valuation, with residue field, let's say F, well then the cohomological dimensions are related. So let me write it here. Cohomological dimension of K is just the cohomological dimension of F plus 1. Okay? This is proved again in Serre's book if you are looking for perfect fields, perfect residue fields. But in general, it's not true, so you have to redefine your cohomological dimension so that this works. So again, you can think of this fact, which is a theorem, as motivation for coming out with the weird definition that he came with. Yeah? Great. So now that you know more or less what cohomological dimension is, I can state Serre's conjecture. Serre's conjectures 1 and 2, I'm not going to state the 1, but they're both related with the behavior of cohomology of linear algebraic groups for fields of small cohomological dimensions. Serre's conjecture 1 concerns cohomological dimension 1, but that's already a theorem. For a long while, it's a theorem of Steinberg in the 60s. So I'm going to stick to Serre's conjecture 2, which says the following. So it says, if the cohomological dimension of the field is at most 2, well then, H1kg, so the first set of non-abelian cohomology will be 1 for every, will be trivial for every semi-simple, simply connected, algebraic, well, simply connected linear group G over K. Okay? So this implies that all torsors over and under this group are trivial. So again, if you're not acquainted with algebraic groups, simply connected ones, examples, SLN, symplectic groups, spin groups, which are the covers of the orthogonal groups. Well, I guess you all know that over here. But anyway, those are examples of semi-simple, simply connected groups. And here there's lots of partial results as well. So regarding this conjecture, there are two ways you can go about it. You can either think, okay, so semi-simple, simple connected groups, they come in families. You got your AN, BN, CN, DN, and all the weird ones, E6, E7, etc. And go group by group, trying to do it for any field. Or you can fix your favorite field and try to prove the conjecture for that field. Okay? Of course, it has to be of cohomological dimension 2, otherwise it's not interesting. So let me try to tell you what has been done in both directions. So this has been proved. Sorry? Well, the conjecture is for any field.
No, but I'm saying since you didn't define what CDK, do we have knowledge of what kind of...
Oh, all right. I should have said that. Actually, the original conjecture by Serre, it's again in that book, Galois cohomology, and of course it's stated only for perfect fields, because at that time, you only had cohomological dimension for those fields. But nowadays, it's extended to any field using the definition by Kato. And actually, you use an even weaker definition. So you expect something stronger than what I just wrote here. Okay? It has to do with separable cohomological dimension, but that one is even more complicated. I don't want to get into those details. Okay? Because in the end, I want to stick to characteristic 0 at some point. So yeah, but I have to speak a little bit about this anyways. So, yeah. So this conjecture has been proved for arbitrary group G over some nice fields. Some of them you might know. For instance, oh, not a good idea. So, proved for arbitrary G if K is, for instance, one example, complete, discretely valued, like in the title. Discretely valued with perfect residue field. Okay, so of course, there's one example of discretely valued perfect residue field that you know. Those are p-adic numbers. So yeah, for p-adic numbers, this is a result by Kneser in the 60s. Okay, but then it was generalized to this context by Bruat and Titz, with all their work on buildings. All the theory of buildings has a very nice application to this context. You can actually prove Serre's conjecture too for all these fields. Okay, so it generalizes Kneser's results. But then there's also, well, a number field. Okay, for number fields, well, this is the work by Harder, again in the 60s. He used his own local global principle for H1 and the results by Kneser to get the conjecture for every group except E8, which was proved by Chernusov in the 80s, 89 if I'm not mistaken. Okay. Of course, when I say number field, it has to have cohomological dimensions more or equal than 2, so it has to be totally imaginary, otherwise you don't get the hypothesis. Okay? If you get a real place, you lose this. So it has to be totally imaginary number field. Okay? And just to give you a non-arithmetic field, you can take, for instance, function fields of complex surfaces. Complex surface. Okay, this was done by De Jong again, Hay and Starr. Okay, so there are lots of fields of geometric nature. There's work by Colotelen, Parimala, and Oyanguren. There's a recent preprint by Olivier Benoit on Stein surfaces, if I'm not mistaken, where he proves Serre's conjecture 2 for those fields as well. So there are people working on Serre's conjecture 2 for geometric fields, fields of geometric nature. Okay, so there's a lot that has been done for a fixed K. Now let's go the other way. So let's try to do for arbitrary K, right? And then we specify the G. So if G is, well, first, the strongest result we have in this direction, you got all the classical types of types AN, PN, CN, DN, but non-trialitarian, so not the weird one, F4 and G2. So you got really, really lots of them, almost all of them. This was done by Bayer, Eva Bayer and Raman Parimala in the 90s, 94, 95 maybe, again Invenciones. Really, really huge result. Although, I must say, with perfect fields again. Okay? This was generalized in the 2000s, I'm guessing 2008 maybe, by Berruy, Frings, and Tignol to the case of imperfect fields. So they essentially followed this proof and dealt with the technicalities of that weird definition that I'm not stating. Okay? But yeah, it's done for every field. I'm not going to write down that reference because it will be moot in a second. But just to give you a second result, it's also proved for quasi-split groups of types, the weird ones. So D4, the trilitarian case, of course, E6 and E7. There's a lot of people that did this. There's Garibaldi, there's Gilles, there's Chernusov, and actually I could not tell which one came first. There's even some cases hidden in the Book of Involutions by Knus, Merkuriev, and Rost, and Tignol. So yeah, lots of people, okay, have dealt with the quasi-split case in these weird types, okay? And now, the last thing I'm going to say, so if you focus on fields and try to go case by case with the groups, we can say the following. That's a recent result with Diego. It's not the one that I want to tell you today, but it makes sense to just mention it here. If it holds for countable fields of characteristic 0, then it holds in general. Okay? And the proof of this fact goes type by type. If you prove it for countable fields of characteristic 0 and E8, say, you get the same result for E8 in general. Okay? So we worked a lot in order to get rid of imperfect fields. We do not have to deal anymore with imperfect fields, and we're glad we don't have to, but they came back, and with a vengeance. Okay? So let me tell you about that. But yeah, what motivates us with Diego is it's Self's conjecture too, but as I'm going to explain now, they are indeed related. So let me tell you something about the relation between these two. Okay? Now, okay. So say you want to tackle Self's conjecture 2, so you fix your favorite semi-simple, simple connected group, and you can start by trying to decompose it in some smaller pieces. So you take, it's not a really enormous piece, but anyway, you can take, add. You can take the center, okay, so this is the center of the group. It's important to know that for semi-simple groups, the center is finite, so it's not a big thing. And you quotient by the center, and you get what is called the adjoint form. So if you take SLN, you're considering PGLN, and the center is mu n. Okay, so it's a nice finite group with which you can try to, okay, so let's study the cohomology sequence associated to such a thing. It's not abelian cohomology, but still, non-abelian H1 is relatively well behaved. So you can try to do some stuff. And you get an exact sequence like this. So H1K G, H1K G-add, and H2K Z. Okay, I'm going to call this map delta. Okay, so you have this exact sequence right here. And here are some facts that come from the classification of reductive groups. So I'm just going to throw it as a fact. Okay, so first fact, there exists a quasi-split group G0 and a class, I'm going to write this way, bracket A in H1K G0 add. So let me stop right here just to mention some things. Quasi-split, I didn't mention it, but in case you don't know, a quasi-split group is a group such that there exists a Borel subgroup defined over K. Okay? So those are nicer groups to work with. That's why you can do stuff like I said over here. Okay? Quasi-split groups are simpler cases. Okay? And any other group, you can obtain it by considering some quasi-split group and twisting it. By what? By a co-cycle. So A is going to be the co-cycle. The class of A is the brackets over there. So yeah, Pierre said it this morning. Sometimes you can consider a class and a co-cycle the same thing. Here is not the case. You have to take the co-cycle and not the class. Sorry? This is a general fact. This is. It works if you take flat cohomology. It works if you want to do characteristic P. It works if you take flat cohomology, and everything that I'm saying is still true. Okay. Great. By the way, here flat and italic is the same because they're smooth. This is the only one that can bring you problems. But yeah, it works anyway. Well, such that, let me end this sentence. Such that G is just your G0 twisted by A. So this is what I call a Galois twist, a Galois inner twist. And why do I call it inner twist? Because, well, this is G0 add. This is just the group quotient by its center. So it's essentially the inner automorphisms of G. Okay? So this is what is classically known as an inner twist of the group G. So every group is an inner twist of a quasi-split group. Great. So look at this sequence again, and let me put just zeros over there. Okay, so the sequence works for G0. So now, if the class, that is a second fact, if the class comes from the left, I'm here, if I come from here, H1 KG0, then H1 KG and H1 KG0 are in bijection. This is classical twisting considerations in non-abelian cohomology, but it tells you then that if you do the quasi-split case for the conjecture to prove triviality of this, then you have the triviality of this. So you don't care about the classes that come from here. So the corollary of all this consideration is that the difficulty lies in this guy. Great. This is what one calls the TITS class, by the way, if you've ever seen that terminology anywhere. Okay? And by the way, this is what you call, if you come from here, this is what you call a strong inner twist, because you're doing an inner twist that actually comes from the group itself, not from its inner automorphism group. Okay? Well, the difficulty lies here. That's great. And so again, we know for all these cases. So we only care about D4, E6, E7, E8. Okay? E8 has no center. Great. No problem. So I only have to do the quasi-split case. It's not done, but it's the only thing that I have to do. And the other three, so this is the last fact that I'm going to throw over there. No, maybe not. Two more facts. So for G0 of types D4 and E7, well, this guy is just mu2. It's just of order 2, it's just roots of unity, plus minus 1. And if I take E6 instead of D4 or E7, well, then this guy is just mu3. So third roots of unity, very nice subgroups. And recall, but, let me put it this way, but H2K with values in mu n is nothing but the Brouwer group again. And it's actually the n torsion of the Brouwer group. Okay? So we're back to the Brouwer group, and we're back to our first problem, that is the one of studying central simple algebra. So now I have to be vague. I'm not going to give any detail, but the point is, the more complicated this class is, the more difficult it is to deal with the case concerning Serre's conjecture. And the difficulty, the complexity of the class has a lot to do with the index. Okay? In the following sense. Let me just throw one last fact that is already well known. You can find it in a nice book by Philippe Gilles on Serre's conjecture 2. So if your TITS class, so this is a class in H2KZ0, has index 2 or 3, depending, of course, on which group you're working with, well, then you get what you want. You get H1KG is trivial. Okay? In other words, period equals index for P equals 2, 3 gives you Serre's conjecture 2 for D4, E6, and E7, which are 3 of the 4 remaining cases of the conjecture. Okay? So there's a nice relationship. Okay? And by the way, of course, the case of, for instance, SLN, you have to deal with PGLN in the end. If you do the same yoga here for SLN, which is a classical case, you're essentially dealing with PGLN, and H1 of PGLN is the Brouwer group again. So yeah, these considerations come from the classical case as well. Okay? But since these are the only remaining cases, I will stick to those. Yeah, I will get. Okay. So that's more or less the relation. So with Diego, we wanted, we still want to solve as many cases as possible of Searle's conjecture 2. We're working on that. So of course at some point we came across all these arguments and we tried then to understand these period index problems. Okay. So let me now go to the main results. Maybe change the, let me try with this one. Okay. Main results. Great. So the big theorem we got here is the following. So let K be a complete discretely valued field of characteristic 0. Okay, so far so good. With cohomological dimension 2. Well, I'm just going to put equal to, otherwise it's just not interesting. Then, well, then period equals index, essentially. So that's what we proved for every central simple algebra over K. Right. So as a corollary, I'm going to put it like this because I'm hiding something under the rug. Well, we get Searle's conjecture 2. So for such K. Anyway, great. So in the remaining time, I'll try to give you an idea of what tools we use to prove this. But there are two remaining questions that you might ask me afterwards, or maybe I'll have time. I hope. The first one is, okay, so D4, E6, E7, what about E8? Because I'm claiming we proved the whole thing. Okay, first one. Second one, I said that I care now about countable fields of characteristic 0 because I got rid of imperfect fields and positive characteristic fields, and now I'm working over complete stuff. Those are clearly non-countable. Why? Well, those are two questions that you can ask me afterwards, but for the time being, bear with me. This is what we proved. This, again, this was known if the residue field is perfect. That's Brouwer-Tit's result. This one, for this part. Okay, the application was known. But for imperfect residue fields, it was not known. That's new. It's still new here. And that, of course, wasn't known either. Okay? But yeah, I'll try to answer to those questions afterwards if I have time. But for the time being, let me just tell you what is the main tool we use to tackle this particular theorem, because that's just a corollary. Well, the main tool is Milnor K-theory. Okay, so now I have to give a definition. At some point I have to define stuff in order to explain you what Milnor K-theory is. In a slogan, Milnor K-theory, I like to say that it's just Galois cohomology made explicit. Okay, it's really, really a nice way of making explicit computations with Galois cohomology. Okay, but of course, and when I'm saying that, I'm hiding a big fat theorem that I will state right now. Okay, but first things first, let me define Milnor K-theory. Okay, so so K-theory of degree Q of a field L. I'm going to take the L so that you don't get confused with the K from K-theory. So this is by definition, L is a field here. So I have three cases. Well, if Q is 0, well, this is just Z. Okay. If Q is 1, this is just L star. So far, so good. And if Q is greater or equal than 2, well, then you just take your K1 and you take copies and you tensor. Tensor. Q copies, of course, because we're taking Q. Tensor over Z. This is an abelian group, so you can tensor over Z. It's the only thing you can do. Okay? And you mod out a relation. Which one? Well, you mod out every symbol, every pure symbol of the form A1 tensor blah blah blah, A tensor AQ, such that you can find two variables, two elements that sum up to 1, with I, of course, different from j. You mod out by that relation. And that immediately becomes quite complicated, because this is multiplicative, great, this is multiplicative, these are multiplicative groups, very nice, but the relation I'm imposing is additive. And that brings complexity. This is a very, very rich thing. It's very elementary, but it's very rich in its complexity. And if you have ever worked with Hilbert symbols or quaternion algebras, you will recognize this. Think about K2. It's just two letters, two symbols, two elements in L star, and you know that if they add up to 1, then the thing is trivial. That's classical computations with Hilbert symbols. So this is a nice generalization of all the symbols that one finds when one works with quaternion algebras and these kind of things. Okay? So one can feel that it is related to what we're doing. Okay? So now the crucial remark that one needs to do is that if I take K1 of L modulo n, it's a group, so I can just mod out n. Well, this is just L star modulo L star to the n. And as you all probably know, by Kummer theory, this is just H1 of L with values in mu n. Great. So now I can cite the big fat theorem by Voevodsky. Only the part of p equals 2 gave him the Fields medal. So, but yeah, it's a lot of people. He was the main one, but he was based on work by Rost, Suslin, Jochowicki, etc. There's a whole bunch of people. But Voevodsky was the main guy. That would tell you that there is an isomorphism as follows. So you take your K theory modulo n, and you go to cohomology, degree q, with values in mu n. You have to take tensor powers here. But again, think of a field that has the nth root, so you need to just z mod n, okay? So don't take that too seriously. It's a nice group anyway. And what do? Well, you take the class A1, AQ. This is just the class of this guy. This guy is just the notation for the class of such a guy. And, well, you take it to, what can you do? You can take the class of A1, cup product, AQ. What am I doing here? A1, it's an element of L star, okay? So it defines a class here. So it defines a class here. It's the element of H1 L mu n, and I'm doing cup product with all the other guys, so I'm going to fall in HQ with Q copies of this group over here, okay? And that's an isomorphism. So now I can compute cohomology classes using K theory, okay? That's the big theorem. So now you can work and do lots of cohomological stuff working with this explicit context. And that is really great. So then, now that's the theorem, so now I'm going to use it. So I care about period equals index for, say, P, for algebras of order P, or period P. Well, this is implied by the following statement. So if I prove that every class in K2L modulo P is a symbol and not a formal sum, that's what I mean. Again, let me be explicit about it. This is a tensor product, so a priori you are generated by stuff like that, but an element, an arbitrary element, is just a sum of symbols, okay? So I'm saying that every element is a symbol, okay? That's a strong statement, okay? And if every element is a symbol, then I'm essentially proving that period equals index. Yes?
I'm very ignorant in this subject, but why this theorem is so important? Why is it so difficult to prove?
Well, what is not hard to see, you can find it in a book, for instance, your favorite book on K-theory, is the fact that this morphism is well defined, first things first. So you have to prove that this relation actually goes to 0. But the hard part is surjectivity. So you're essentially proving that the cohomology ring, if you take the direct sum of all the Q's, with respect to cup product, is generated by H1. So you can understand all your cohomology only by looking at H1. Okay, that's the strong statement. Okay? Higher cohomologies don't tell you as much information as you thought. H1 controls everything.
This part that we want to do with K theory.
Sorry?
I'm just saying what you just said, the subjectivity
Exactly, surjectivity, of course, of course.
Nothing to do with K theory. Like, no, the way you said it, apparently, like, just some HQ is generated by H1, it's just unit map.
Sorry, I'm not sure.
These brackets, they're elements in H1, right?
Yeah, yeah.
So that's just, I'm not saying it's easy, I'm just saying you don't have to know what's HQ to prove subjectivity. If you're just good with cohomology, you can do it.
I'm not sure about what you're stating, actually. I'm sorry.
He's saying
It's just,
that
it's
if
just
you
cohomology, there's no K theory on the subjectivity. Because these H1s, if you admit the remark, right,
Yeah, sure.
then the subjectivity is just a statement of how you can generate HQ instead.
Exactly, that's fine. But that's the hard, actually subjectivity is the hard part of this theorem. Indeed, that's my point. I mean, I was translating the subjectivity is the hard part, and what subjectivity is telling you is essentially what I said.
But you're saying like conjectivity is not your part.
No, it is. but that one's readable. The subjectivity part actually needs the whole theory of splitting varieties. That is the whole point developed by Blavatsky in order to actually deal with the whole thing. Again, he won the Fields Medal only for the case of n equals 2. Okay? And then, since it's mu2, you can just put z mod 2 everywhere, and that's simpler. And yeah, that was Milnor's conjecture. The cohomology with coefficients in z mod 2 is generated by H1. Okay, and that's non-trivial. And you need the whole theory of splitting varieties that then was generalized to the case of P. Actually, this case is known as the Bloch-Kato conjecture for arbitrary P. And yeah, so the case of P equals 2 is just the Milnor conjecture. But yeah, that's the hard part. Something that was known before, and actually is the only thing that I'm going to use, actually, is the fact for K2. For K2, so you can know that, yeah, if you take only K2 and H2, you're saying essentially that the Brouwer group is generated by quaternion algebras. No, cyclic algebras in general, cyclic. So the two torsions generated by quaternion algebras, that's classic. But the fact that the Brouwer group, the P torsion of the Brouwer group is generated by cyclic P algebras, well, that's Merkurjev-Suslin's theorem. That comes quite before. That's from the 80s, whereas Volgevodsky, it's the beginning of the 2000s. So it's 20 years later. Okay. But yeah, I'm essentially using Merkurjev-Suslin, so I could have avoided all this, but because I'm using only K2. Okay. But if you prove this, then you're proving that essentially, yeah, H2, so the Brouwer group is generated by cyclic algebras, so the generalization of quaternion algebras to the P part. And if I do that, well, cyclic algebras are easy to deal with. They do have period P, and they do have index P. You can prove that explicitly, because they are explicitly constructed. They are of size, P times P. So yeah, so if you prove this, you prove this. So this is what we wanted to prove. Okay? So when I said that we proved period equals index, what we actually proved is this. We proved explicitly, we took any class in K2 mod P and proved that it actually reduces to a symbol. Okay? That's what we proved. And then there's abstract nonsense to reduce from n to powers of P and from powers of P to P. We have to cite other people, of course, but this is the crucial part, the P part. Okay? Great. Yeah, I think I'll manage to do everything. Okay. So now, let me give you an idea how you do this. Okay? First, the easy part. Okay? The classical part, the one that everybody knew before us. So, if now K is, well, let me just say as before, completely discretely valued, characteristic 0, residue field arbitrary. Okay? So F, the residue field. Okay, you want to prove this. And let us start with the easy case. So let us assume that P is not the characteristic of F. Okay, that case, okay. So there's this nice exact sequence in K theory for complete discretely valued fields. It goes like this. So you get K2 of F, you get K2 of, oh, I'm sorry, I used K again. Well, I hope you understand. And you get K1, sorry. K1 of F mod P and 0. So you can understand K2 of K mod P if you understand the K theory of F. Okay? But now I can finally use the fact Okay, so my field has cohomological dimension 2. And as you might recall, the only thing that I wanted you to remember is that the cohomological dimension of the residue field is 1 less. Don't care about the definition. Okay? The important part is that this guy is 1. And that has consequences. That tells you that this group disappears. Okay? Again, there are relations between K2 and cohomology. So just imagine, okay, this is telling me that the Brouwer group of this guy is trivial, so this must be trivial. Okay? So you get an isomorphism here that is called the residue map. And the residue map is quite explicit. So it sends, for instance, the class of pi comma u to, well, the class of u bar. Okay, so what is all this stuff here? So again, u bar is in f star modulo f star to the p. Okay, so u bar is the image on the residue field. So I'm taking pi a uniformizer here. And u a unit, so u in O k star. Okay, so that I can take actually u bar and make sense. So for such a symbol, it gives you this. So what I'm taking in return, okay, so every element here, of course, is just u bar for somebody, u bar and f star. So what I'm telling you is that every guy here has this shape, pi comma u. So everyone is a symbol. Okay, so that's the easy part. So every class is represented by a symbol of the form pi u. Okay, so that's the easy case. Of course, what's the complicated case? When, and this is where I told you that they came with a vengeance. We have to consider an arbitrary field f. So we have to consider imperfect fields of characteristic p, okay? And in that case, well, this does not work anymore. This is false. This is utterly false. So we have to invoke once again our dearly friend Cato. So Cato gave same paper, definition of cohomological dimension, fact about discretely valued fields, and this description all in the same paper in the 80s. An explicit description. Again, this is what is nice about K-theory. It's explicit. You can do computations of KQ of K mod P in terms of differentials. I told you they will come back. Okay? So differentials in the sense, just absolute differentials, omega n f, which is just the exterior power of omega 1 f, which is just the classical symbol. You just take dy for yn element in your field. That's it. Okay? So with this, you can do explicit computations. And by the way, so the fact that you have cohomological dimension 2, again, it tells you that you have cohomological dimension 1 on the residue field. And this tells you that your omegas are very nice. So omega f r is 0 for every r bigger or equal than 2. And omega 1 and omega 0 are really nicely behaved. You can have some control on them. So you conclude with well, long, tricky, of course, explicit computations. So that's actually the whole paper, essentially these computations right here. They're full of nice tricks and stuff. So I'm not sure if I started at the right time.
You have 6 more minutes.
Okay, oh great, great. Because that's essentially the idea, okay? So this is the complicated part. You really don't want to read that. I really want you to feel that, okay, so there's a period index problem and SAS conjecture 2, and they are related. So it's really, really interesting to prove these kinds of things. So now that I have some time, let me just tell you about the 2 things that I promised. Starting with E8, okay? So this is just sheer luck, okay? So a word on E8, okay? Because I told you, okay, so we proved period index, so what? We get D4, E6, E7 for SAS conjecture 2, we're missing E8. Well, here's something that has nothing to do with the talk, but this is a question by Bogomolev. Okay, an open question. Nobody knows the answer. But okay, so take K a field, arbitrary field again, any field. Okay, so is the cohomological dimension of this guy smaller or equal than 1? By this I mean maximal abelian extension. Okay, so that is a wild question. So evidences. So I assume that this is the only evidence he had when he asked the question. Well, p-adic fields. Or number fields. Okay, and this is essentially what you all learn in your course of class field theory. Because class field theory tells you how to control the Brouwer group of these guys. And if you control the Brouwer group, you know for p-adic fields that any class in the Brouwer group is killed by an unramified extension. So if you go to the maximal abelian extension, you will kill everything. And once you know that you can kill every class in the Brouwer group of every finite extension, well, you get this as a consequence. Okay, it's a criterion for cohomological dimension. So that's for p-adic fields. And of course, number fields, well, global class field theory tells you, okay, you control these ones, you control this one. So the maximal abelian extension will give you all the unramified extensions locally. So you're killing every class in the Brouwer group as well. So this is true for p-adic fields and number fields. I have absolutely no other examples that are not of this fashion. I mean, there are some other class field theories for other weird fields nowadays, and you can get the same consequence, but that's it. Personally, I think it's too wild to be claimed to be true, but here's what I think is a more innocent, more provable conjecture. So a more believable, oh, we're in horrible, sorry. Believable question. So is this guy of cohomological dimensions more or equal than 1? And of course, here I'm saying maximal solvable extension. So this guy is bigger. Taking bigger extensions actually reduces cohomological dimension. It cannot grow. So that one I believe personally. And the fun fact is that this implies Serre's conjecture 2 for E8. If you prove this, you get Serre's conjecture 2 for E8 for that field. An observation made by Gilles that you can find again in his book on Serre's conjecture 2. And this is easy. It's very easy to prove for our fields. Okay, so you take a complete discretely valued field and you just take the maximal solvable extension. You can prove, again, more or less in the same fashion for p-adic fields, that everyone gets killed in the Brouwer group, so you're essentially doing this. Okay, so it's just a gift. So we actually proved Serre's conjecture to in all generality for these fields, thanks to that last fact. And I guess I'll stop there. Thank you very much.
Questions for the speaker?
Yes, in your main theorem, you were working in characteristic 0.
Yeah.
But it was uncountable, as you said.
Oh yeah, great question, yeah.
And I wanted to know if you can still conclude something about the positive characteristics case.
In this, but in the complete but with positive characteristic, right?
Yeah.
Okay, we actually tried. It's not at all easy. When we finished the paper, we were like, okay, maybe we should try the equicharacteristic case, because of course characteristic 0, you get it. It's the easy argument I get before. And you were like, okay, well, probably the equicharacteristic case in characteristic P should go as well. There are nice descriptions of K theory with differentials. Of the Brouwer group, sorry, using differentials in characteristic P, and you just, okay, you get your hands dirty, and we couldn't. It is actually quite hard. But funny thing, in characteristic 2 is immediate. Not only that, we actually proved that if you have an imperfect field of characteristic 2, such that the p basis, the 2 bases, so the degree of imperfection, I don't know if you know what I'm talking about. Say you have a transcendence degree 2 over a finite field, for instance, that thing. Those fields will immediately satisfy period index as well. Any field of characteristic 2 such that I have a p basis of size at most 2 satisfies period index. That was some weird computation we did. We were trying to do the p case and we figured that 2 was simpler. We tried with 2 and actually the only thing we used is that. But that argument falls completely down in general, so we have no idea. We tried and it's subtle. There are tools. I mean, there are tools that describe pretty well this. So maybe if someone is brave enough and tries to do the computations, I do believe it's true. But we didn't manage, and since we only care about characteristic 0 fields in the end, we stopped there. So, but yeah, that's it.
Why do you believe in this question?
Oh, you know, well, at some point when I had time, I started thinking seriously about this question, and I tried to build counterexamples. I haven't been able, of course, but I figured that the first thing you need to have is to have enough roots of unity. And once you have enough roots of unity, you start believing this thing. But that's the problem. You need to add the roots of unity first, and then do abelian extensions. That's why I believe this one. But that's it. I don't have evidence. Well, I have this one, but yeah, that's my feeling about it. You really need first to have roots of unity, and then you can do everything else. And then it seems doable, but it's complicated. Even for function fields of curves, I've tried for a while. We tried actually to come up with transition theorems. Like if you add a transcendental variable and you assume that this is true and stuff like that, but you're immediately dealing with Galois actions on Jacobians of curves, and so in the end it's the Galois action on the torsions of abelian varieties, which is of course quite complicated stuff. So yeah, it's not at all a simple question. But again, you do need roots of unity. That's my conviction. And yeah, of course, in those cases, roots of unity are given by the maximal abelian extension, and you're good to go. But I think it's really coincidental in that case. I don't believe it to be true in general.
Sorry, could
Yeah?
you remind us what the E8 group is?
Ooh, you want the equations?
Maybe I
No.
missed it.
No, I'm sorry. Yeah, the classification of semi-simple, simple connected groups, well, they count in these families that are given by the root systems, you know. And there are these classical root systems, the infinite families, AN, BN, CN, DN, that will give you SLN, symplectic groups, orthogonal groups, and this kind of stuff. And you have the sporadic ones. There are E6, E7, E8, F4, G2. That's it. Each one has their complexities, and the most complicated one is always E8. Okay, but it's a really complicated group. It's related though to for people that do lattices and this kind of stuff, there's this E8 lattice. Well, it is related with the root system of this E8 right here. It's a really complicated thing, but yeah. Myself, I don't know either any equations, or I'm not particularly fond of that group. But yeah, that's why this I don't like, but this I like. These kind of questions I like, so I like to work on that. And as far as I know, somebody already proved that it's enough. I'm good with that. I'm not an expert at all on E8. I'm sorry.
A big question, so it's about, I'm a bit confused about the state of art of the circle conjecture number 2. I mean, what is the next? What is a lot of proof?
Well, again, you had these two approaches, going group by group or going field by field, right? But of course, trying all fields like one by one makes no sense. So people usually tried group by group, and that's what Byron and Parimala did. And then you have all these weird cases where you have the quasi-split case, but not the general case. And you have a lot of techniques that they all go in the same way. You start with a torsor, and you pray for it to come from a subgroup. And the subgroup might be nicer, maybe I already treated it, and I'm good to go. That's the main idea. But to manage to get it to come from a subgroup, you have to add hypotheses, and there come the technicalities, etc., etc. I tell you, there's this whole lecture notes in mathematics by Philippe Gilles that gives you all these techniques. That's why with Diego, we tried to come with another approach and say, okay, let's try to actually move the field. And we proved this statement that if you know it for countable fields characteristic 0, then you get it for every field. But that's a complicated construction because you have to keep, and the problem moving the field is that cohomological dimension is wild. If you change the field, chronological dimension might explode, just taking subfields. So yeah, you have to develop nice techniques so that you can actually get subfields and you can reduce to them with the correct chronological dimension. Actually, we wanted to prove, we weren't able, instead of countable, we wanted to say finite transcendence degree over Q. We really believe that to be true, but we haven't been able to get there. And once you are there, you want to start from Q, then Q of t, then Q, start adding variables and see what you get. So that's where we are right now. That's actually, yeah, let me just tell you this, I'm sorry. But I have to tell you. So we started from the other way around. Q, check, great. Q of t, no idea. First of all, it has chronological dimension 3, but say algebraic extension of that with chronological dimension 2. No idea. Okay, let's leave the countable world for a while and let's do QP of t. Maybe that's easier. No idea. Okay, let's complete again. QP double parentheses t. That we can do, and it's done. Great. So let's try to do some local global principles to get to QP of t. There are local global principles. Okay, problem. Local global principles need other completions of QP of t. Those are completions in the p-adic valuation, and those are discretely valued fields with imperfect residue field. So we're back to this. That's how we came here. That's why we want to prove this. Next step, local global principle, try to prove it for algebraic extensions of QP of t with chronological dimension 2. If we get that, maybe one day we might get Q of t, and then go on. That's a long road we have ahead. But from the other side, you want to get to finite transcendence degree. That's where the two things collide and you have the whole proof. But that's a whole other method. That's the point. I mean, the state of the art is what I gave you. And basically, it's stuck right now. The group by group approach is stuck. And it's really, really specific, so nobody wants to go in there. That's the problem. So that's why we're proposing a new approach, but that's what we get right now.
Is there anything we can or would like to say about fields with high chronological dimension?
Ooh, that's a nice question, but that's a whole other talk. Actually, with Diego, we proposed some higher Serre's conjectures for higher chronological dimension. But we have to weaken the condition. Instead of having a rational point, which is a good condition for a torsor to be trivial, we said having a zero cycle of degree 1. That is a condition that you can state in terms of K-theory. And then you can grow the degree of K-theory and at the same time grow the chronological dimension. But we actually proved that those, in the end, we proved that they were equivalent to the first one. So, I mean, if you prove the first one, you're good. That's the point. So there are higher Serre's conjectures, but yeah. They're essentially done with if you do the first one. So, yeah, so that's pretty much done.
All right, let's thank Giancarlo again.
Thanks. Oh.
Have an easy example of a number field with chronological dimension equal 3, for example?
No, actually number fields, it's either 2 or infinity.
Okay.
That's it. Totally imaginary, 2, otherwise infinity. And the problem is the reals. The reals have infinite chronological dimension. So if you have a real place, you're done. That's all.
Thank you.